consider for a particular example here, I pick this system, but you can apply the knowledge to other general type of the second order systems. And I will give you the reason why we pick up this one. Okay, we particularly will pick up the system, and the system is like this, and that is the second degrees in the denominator polynomial, and this is our output, and this is our input, and R over S, and we consider a unitary feedback here, so minus plus. Okay. And this is a very particular second order feedback control systems. And the reason why we want to pick this up for demonstration, because if we write it out, the transfer functions, y over r, that one can become like omega n squared, s squared plus 2 zeta, omega n s plus omega n squared. Because this one, the transfer function will give us what we call the standard form of the second order systems. This one is exactly equal to the one you've been familiar with in controls. Because we wish we talk about this one based upon the standard expression, so we pick this one. Okay, but in general, the terms we learned, we should be able to extend it to other ones. So later I will make a comment to the general systems. Okay. So now for this case, if you like, and we can have the say unit impulse response. Unit impulse response, you simply set R equal to delta, and then you can calculate. Okay, and unit impulse is not that important for the second order systems. So here we directly study is the unit step input. Okay, so we directly study this form. So now for this case here, therefore we have the y will be equal to, let me rewrite this one. So how to get the yt? And yt simply is the inverse of y. And that one, the process is in the one handout I gave it to you, I think a couple weeks ago. So look for that one, and then again, if we have a numbers, basically, if we have a numbers, then you can do the factorization, you can split the two terms, and then etc. Okay, so let me write it up, and this equation is written on your handouts, on the top of your handouts. Let me write it up here. So that will be equal to 1 minus exponent and very long equations. Okay, so that is this equation here. And for this equation, you can see we can try to draw the response. So here, let me say this is 1 here. Okay, this one defines the level of our unit step input. Okay, so basically we want to look at how system is going to follow up, how quickly the response of the system is going to approach to 1, and eventually or in the transient response here. Okay, so again, to do this one, we should be able to use MATLAB to plot something, and I don't know whether you know how to use MATLAB. Are you Are you comfortable using MATLAB to say, if I ask you, if I would give you the parameters, okay, I give you zeta, I give you omega n, etc. How comfortable you feel to using MATLAB to plot the curve? Can you do it? Or otherwise, I can quickly show you here. Okay, let me show that right here. We unify everyone on the same page. So let me make one example here. So for example, let me say omega n equal to say 10, okay, and zeta equal to 0.2, and we have all these things we did it. Okay, so that is a given input. So maybe in MATLAB you can produce a file, M file, okay, and in there you can define the functions. So you can define the function y equal to, here is the definition of a function and mouse characters, okay, and that is a function of time. And then you begin to write the function here. So of this function, and leave a space here, and 1 minus, what do you call, 1 divided by square. Then I'm going to write this one first, okay. It's QRT, and 1 minus, and how about let me using Z for zeta, okay. So let me use Z for zeta, okay, so that is zeta. And Z times Z. Okay, basically this one is to take care of this term here. Okay, and then I'm going to take up this term and times exponential, which is a functions, and minus zeta times, let me replace omega and using W, okay, so that is omega n. So Z times omega times T, and right now everything is defined constant except T, but here you define T as a parameter, so MATLAB will accept it. Okay, and now multiply, right, I'm going to write into that one. Sine, okay, that is, if you come up with a line, you can continue, or you can put the 3 dots, tell MATLAB this will continue to the second line. And here, let me multiply. Okay, here is multiply. And sine, that is the functions. Okay, sine function is omega times SQ RT 1 minus V squared times T plus, this is arccosine, ACOS, and Z. And for zeta here, you must be in radian. Okay. No, sorry. No, never mind. Sorry. In MATLAB, there's a 2 arccosine, and here will give you a result of radian. If you, on the other side, you're using arccosine d, then the MATLAB will give you in terms of degrees. Okay, but this is not. So that is for this one then. Okay, so now with this one, then you can begin to say sine t, how much you want to calculate. For example, from 0 to say to 10 seconds, okay? And then you want to have an increment and say 0.05 as the incremental step to 10. So then you put it in here. Then eventually then you have everything, then you can plot t, which has an array of the value here, and then yt. And that is MATLAB will give you the curve like this. Okay, so we plot 1. So that will be something like this. Oscillating. During the oscillation, also decaying. The decaying profile is given by this. Okay, so this is the decaying profile. The same thing. Okay. So eventually, given depends on those parameters, eventually the system is going to, so let me continue. Eventually, the system is going to oscillate very close to the certain range, say 1% or 0.5%, depends on how you're going to define it. So eventually, the system is going to converge to the steady state, which is equal to 1 here. So 1 is our input. Okay, so eventually this eventual response. So this is we call the transient response. This one is called the steady state response. And for second order system, most of the time we are interested is in the transient response. We want to know how quick the system will be, and we want to know how quick the system, how good the system behave. And so here we have certain characteristics. The first one is this value here. So this one, for the first over peak, we have quite a few peaks. The first peak is always the worst one. Okay, so here it's called the over peak. Over peak is the magnitude larger than 1, and that one is designated by okay, so that is the over peak we're using the symbol NP. And corresponding the time we arrive in is called the TP, when the first overpeak, when the first the NP arrives. And also we have the rising time. So that means when the system first hit the value of the input, then we call the TR. The R means rising. Rising time. And TP called the peak time. And sometimes, in particular, the people likely interested is halfway to the 1. So here the corresponding is called the T, D. D means delay time. So right now today you can put the names onto those transcripts and the settling time. So eventually the system response going to fall into a range, certain range, I would say 2% or 5% or whatever the percentage you define it. Okay. So that means once the magnitude of the system oscillation falling into a certain defined range, with this, different discrepancies from this, the input. So that time is called the TS. S, that means settling time. The system's value is going to settle. Okay. So 1, 2, 3, 4, 5 parameters. Next time coming back, and Friday, Wednesday we have a test. So Friday we will continue to give more quantitative descriptions of those things. Good? Okay, so that's it.